Alright guys, we're going to start with some EM spectrum and some waves basics. So the EM or electromagnetic spectrum are the poorly written words there. So radio is the longest wave up through gamma. So you may need to pause this and write this down, but these are your vocab words that you need to understand. So the EM spectrum and waves in general are specific to physics. So if we look at the question at the top, the essential question, how can energy move in space? And what are waves? So those are the two questions we're going to answer in these notes. They're going to go pretty quick, so you may have to pause them as needed. These waves are not the kind that you would ride, like if you think ocean waves, but they kind of move the same and they move energy. So like with the atomic structure, waves are broken into pieces, and we're going to focus on the first part here is a light particle. So the light particle is a particle that produces a specific light pattern. It's sometimes called a photon. So if you watch or you know anything about sci-fi, sometimes they say, photons. And these are just beams of light. They travel the fastest in a vacuum where there's no gravity. So the vacuum that we would associate with would be space. And the parts of these light particles are the frequency, the wavelength, and the velocity. So up here on the top right, we have a wavelength, which is from top to top. So this is how I measure. Frequency is how many go by in a specific time frame. And the velocity is the speed that it goes by and the direction that it's moving. So frequency is the number of waves that pass by a reference point. So just remember back on physics, we had a reference point, the place that doesn't move that we count by. Frequency is usually measured in a period. So if you look over here on the left, we have low frequency, a medium frequency, and a high frequency. This means that the amount of wave that goes by in a specific period is low because there's one top, two top, three top. If I look at the medium, 1, 2, 3, 4, and part of a 5, so I'm increasing it just a little bit, and then frequency that's high, 2, 3, 4, 5, 6, 7, 8, almost 9 there. So with frequency, it's how fast they go by in a specific time frame. Shorter wavelengths usually mean I have a high frequency. So if the time between each wavelength, which is from top to top, is short, meaning it's short time frame, then that would mean I have a high frequency. If I have a long wavelength, meaning that from top to top is greatly spaced out, then I would have a lower frequency. When I count frequencies, I'm going to count crest to crest. So this is really top to top. So if I look at the picture there, the crests are the tops of these waves. Now the trough, and that is T-R-O-U-G-H, but it's pronounced T-R-O-U-F, trough. These are the bottom parts of the waves. So you may need to put this in your notes if you cannot remember that. Amplitude is from this resting point, from the point of reference to the top of the crest or to the top of the bottom of the trough. It depends on how you're measuring. Amplitude, we just said it, is the height or the to the crest or the depth to the trough. So how high up does it go or how low down does it go? Visible light, this is the part that most of us enjoy to look at because this is the part where we see. But it is actually a very tiny part of the EM spectrum. It's the only part that we can see or be detected with our normal human eyeball. The colors ranging from low frequency, meaning that there's a long wavelength, is red, and then the highest frequency, meaning that the short wavelength, is violet or purple. So looking at the EM spectrum, you may need to pause this. Radio is the longest. Microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. There is a link to a song that I'll put in the description down below. But this is a really neat visual, so if you are really good at drawing or you see things in visual perspective, you may want to go search for this picture on the internet. But it tries to associate the length of the wave with the size it would be in natural surroundings. So if you look, this is a fairly tall building, and that from the bottom of the building to the top of the building would be about the length of a radio wave, and that's the radio waves that our music travels on our, like when we're driving down in the car down the street. Microwaves are about the length of a honeybee, so they get substantially smaller, and they get small really quick. The microwave is one that we use to heat up our food. But then if you look down here with like X-rays, these are like if you get your bones looked at, those are the width of an atom, so they're really, really tiny. So let's keep going. So what is an electromagnetic wave? And then the sponge is actually your extra credit for this week. So if you wanted to copy this down and put it in your notes, or give it to me on Friday with your quiz, then this would be some extra credit points. So here's the video that I'll link in, and this goes in with all of the EM spectrum waves from radio up through gamma rays, and it has a kind of catchy tune, so that'll be in one of the links. The EM spectrum, the waves have an electric charge, and they have magnetic properties, so they move like up and down and side to side at the same time. They're arranged by frequency or wavelength. So as I increase I decrease my wavelength, meaning I make it smaller, I'm going to actually increase the amount of energy. So if you think radio waves, I can stand by radio tower and nothing really happens to me. And then I go up here to gamma rays, and this is like the dangerous end of it. Each wave has different properties, and that's why there's a distinction between the waves. That's why there's not just, it's all electromagnetic waves. And they all travel at the speed of light. So EM waves do not need matter or a medium or stuff to transfer energy to. So this is why, like, if you have a radio in your house, you can move the radio around your house and still pick up that frequency. This is also why if you ever go get X-rays, they make you put on that weird vest of lead, because the waves move through everything. They don't need a medium. This is the sciencey word for stuff. They travel in a vacuum. So unlike sound and water, water waves need a medium, which is water, to actually move their energy through it. And then sound, if you go out into space and you yell or you scream or something blows up, you can't hear it, because those sound waves actually need friction and gravity to vibrate against to make sounds. And then they all travel at this 3 times 10 to the 8th power meters per second in a vacuum. So this is actually the speed of light. So radio waves, we're going to go this really quick. Radio waves are used in radios and cell tower communications, and also in heart rate monitors. These are not very dangerous, which means we can stand near them. Microwaves are a little bit longer. They're used in a microwave. They excite or charge up the water molecules in your food. They're used in Bluetooth and wireless internets, and then sometimes in radar and in GPS. So these, again, are not very dangerous because we can stand near them. Infrared, this picks up heat. It's kind of like the heat in your body. They're longer than a microwave, but not as long as visible. We're getting into visible light. These are used in night vision goggles, and then remote controls, and then even in heat-seeking missiles. So this has a pretty big global impact. Sometimes you can see some of these waves coming up off the concrete on a hot day, if you've ever driven up a hill and you can see the little waves move up. Visible light. This is the one that we all love, or most of us do. It's the type that we can see with our human eye. Violet or purple is the highest of the frequency, which means it moves faster. The frequency goes faster, so the wavelengths are shorter. And then red is the slowest of the movers. So I say slow. It's really just the lowest frequency, so that means it has a longer wavelength. Ultraviolet is shorter than visible. They're used in sterilization of medical equipment, and then also now they're being used in sterilization of like pedicure, and like if you go to the nail salon to get your nails done, they would be used to sterilize those equipments. They're used in water disinfection. When they go into areas where there's been a natural disaster, they can help clean the microbes and the bacteria out of the water. And then security marks on money. So this is a security marker for a European country. These are some of the water purifiers that they use. They give these to people. And then this is the dangerous side of UV light, is if you get too much UV or ultraviolet, it actually can damage your skin cells. And if you get too much damage, then you can get skin cancer. These are my friend's feet, and I laugh at him every time I show this because he forgot to put sunscreen on. X-rays. These are tiny wavelengths with a high amount of energy. So this is where they become dangerous. They're used in medical imaging, which is another word for saying X-rays, and then airport security. The men and women that work at the TSA with the airport security, they use X-rays to detect if there's dangerous substances in your suitcases. Too much exposure to this X-ray wavelength can be damaging to your internal tissues. And then gamma rays. This is another fun one that most people like. This is the highest and most dangerous EM wave out there. So this is the smallest wavelength. They move really, really fast. And they originate out in space, but now they can be made in labs, where in labs they're using them for food sterilization. Much like with the water, they get rid of bacteria and fungus and microbes that can be harmful to people. And then they're starting to use them in cancer treatments. So down here in the picture, they're actually going to shoot a very tiny, tiny gamma ray into this person's head to get rid of cancer. So instead of it being long and drawn out and very painful, this is a way to shorten their recovery time. So this is like a sum up of them all. So you may need to pause it on this site or on this part. The visible light can be seen with the human eye. Ultraviolet or UV can cause skin to darken and cause skin cancer, skin damage if done over time. The ozone layer protects us from most of this UV radiation, and sunscreen helps protect us from the rest of that would get through the ozone layer. X-rays pass through almost anything. It cannot pass through dense bone. So if you look at the little crazy bunny over here, the reason that the bones show up is because they're dense. When they're broken, they show that fracture. So it shows up pretty easily in an X-ray. Gamma rays can penetrate everything. That means they can go through everything, even to the point where they severely damage your cells. Infrared are responsible for helping us. The heat that we feel, this infrared from the sun, gives us some of that radiation and that heat. Heat-seeking missiles are used with this in tanks and aircrafts. Microwaves, I know I'm reading this almost directly from the thing. Microwaves are used to heat our food. They cause the water molecules to vibrate in our food, which means that they heat up. They're also used in communication, remember, with the Bluetooth, and then in radio towers, like for communication long ways. And then radio waves are used in TV and radio signals. So that's how you get your TV signals. And they use antenna. So part of your review, if you didn't do this in class, will be to answer these couple questions. What is the relationship or the link between wavelength and frequency? That's the first question. Number 2, what do we mean by spectrum? And number 3, what does Roy G. Biv mean? So I'm going to give you a second. The relationship with frequency and wavelength. Usually the longer the wavelength, the lower the frequency. So short wavelengths, higher frequency. Spectrum just means a broad grouping. Roy G. Biv is red, orange, yellow, green, blue, indigo, and violet. And then these harder review questions are going to have to be done on your own. So what can you actually see X-rays if you were in the room? Which color is more energetic or moves more energy, a red or a yellow? Which type of wave travels faster, gamma or radio? And why are microwaves more dangerous than radio waves? So that's it. I will see you in the hallway. Please feel free to go back and forth and pause and rewind as you need. Thanks.